So another sort of version of this is I'm hoping that this will be an introduction to CNC that finally makes sense. That's sort of the hope, because I think in the past, the people here who have seen Intel's concurrent collections abstraction have found the vocabulary somewhat terrible. So hopefully this is what we're going to do, but I'm going to frame all of this in terms of my...
Unnecessarily creative.
Yes, novelty in the wrong way. So I'm hoping that by the end of this talk you'll understand CNC, and I'm also hoping to get some feedback on my model of CNC, which I've changed and extended and altered based on my own needs from the original CNC model. So for those of you who actually do know CNC, what I'm presenting now will be CNC, but I've made changes, and I'm only going to be presenting my model as opposed to the one that's currently published. So right now, what I'm working on is implementing these CNC extensions and enriching the CNC language, which is it's basically like a data flow programming model. You can think of it as a coordination language. I'm trying to enrich it so we can do more analysis on the language. I'm doing that partly by combining APL with CNC to form sort of its own language. And I'm trying to build more formalism around the CNC model. Hopefully, and our target option right now is to optimize streaming programs. So I'm hoping that we can do some things with streaming optimizations in CNC programs. So what kind of got me into this, and the motivations that I hope you keep in mind throughout this, is I kind of wanted to think about what programming language I would actually use, or what did I really want to use, especially how do I do parallel programming the way that I might want to do it. And I wanted to be able to make certain ideas very clear when looking at the code rather than having them buried, and I wanted them to have very good rigorous expression. Something I really didn't like in existing models is this sort of explicit parallelism. Like if you think of Silk or these threading models, p-threads, or any of these things where you have to manage these locks, handle concurrency, all this sort of stuff. I wanted something that gave me some flexibility like those models, but that didn't make me implement my own operating system just to get, you know, two forks to work without crashing each other. And one of the ways I wanted to do this is make all the parallelism implicit, or at least make it easy to leverage implicit parallelism at the right levels, rather than having way too much parallelism that we can't parallelize very well. And to avoid making parallel programming the main thing, I still wanted to be thinking about the ideas that I'm working on rather than thinking about what I'm programming, the mechanisms I'm using to do the programming. So rather than get into the standard approach of CNC, which is to start with this whole vocabulary dictionary introduction of what CNC is, I'm hoping we'll just start by taking an example and writing a CNC program with the game of life. And this is the classic APL example. So to start with, I want to sort of pretend that we're all APL programmers here. And start, let's see, I'll try to use this side of the wood. Start with what we might write at the beginning, which is our function to compute the next generation of the game of life. And so we're going to get in the previous generation or something like this. And what we would normally do is we would compute the neighbor counts. Let's do NC. And we would compute the neighbor counts by grabbing all the different rotations, up, down, left, and right, of this matrix and summing them all together. So we would do that by doing something like this. And so that grabs all the rotations. And this is the sum of the unravel of the cross product of the left none and right shifts of the left, right, and left shifts of the rotates along each. What we generate here is basically our original generation P, and then all the different P's shifted over and up and so forth. So you don't have to worry about too much of what this does. I'm just using this to sort of, so when you see it again in the future, it won't be too confusing. But basically, we're generating this box, we're unraveling, and then we're summing it all together to get another thing. And so to compute the next generation there, we would take that and we compare that. This is just computing the rules of the game of life, where we have a 3 or 4 neighbor count. And actually, it should be NC here. And that computes our game of life. So basically what this function does is it splits up, it does all the different types of rotations that we could on the matrix, then sums them all together, and those sums, assuming we've got a Boolean matrix, then form a neighbor count. And that neighbor count, we check whether they're 3 or 4, and then we basically pick the new neighbors based on what we get. And this is how we might write it in just plain APL. Or you could imagine any other programming language that you write in here. We've got something here, but the problem is there's a lot going on here, and I might not really know how to parallelize this. What I really want to do is I want to take this and I want to turn it into a parallel program. So when I parallelize this, this is, if I want to compute multiple generations of the game of life, this is basically a stencil computation. And I don't want to really know too much about all the different stencil optimizations that go around, but I'm okay with a few requirements. For example, if I stick with a data parallel type of model or a definition of the game of life. So for example, this definition over here works for any size grid, and that's important. And if I can say that I can work on any size grid, then I can let, hopefully, my computer do the slicing for me, or I can have a knob that I can twist and control the slicing and the partitioning. So in a stencil computation, what we'll do is if we've done this and we compute the next generation, so this is the first generation, we compute the next generation of the game of life, and then we keep going here, and this is, say, time or something like this. We can slice up these matrices and dispatch each of these on different nodes or different processors or other things like this. So it's a fairly simple tiling approach that's common in parallelization. And CnC allows us to do this by drawing a graph of how the computation should work in terms of what data it writes and where it writes to. Hopefully, CnC just allows us to sort of express this idea without actually dominating the main thing. It shouldn't become the main computation. We shouldn't be programming these CnC graphs all day long without actually doing anything on the root level. So let's take this and then imagine what a CnC program might look like. And we're going to start by drawing the graph of this CnC program. So to begin with, we've really only got one piece of data that we have to worry about. There's one block, and we're just computing this giant 3D array. And so the shape is going to have basically the first row, or the first dimension will be the number of generations, or the current dimension you're on. And then you've got rows and columns on here, right? And so each generation will be one of the matrices are one of the generations of this life game. And we want to put some data in there. We want to seed it initially with our initial game of life, or our initial world. And we're going to have to do something to control how that gets in. And this is our projection function, which basically tells us how to get the data into this array. And when we're done, we're just going to take, let's do H. And when we're done, we're going to project this back out. So we need some way to tell what in this array we're going to grab back out. And I also call this a projection or a mapping function. And so this is the basic data traversal across this array. But we need to actually do things to this array to build up or fill up the elements. And that's where our little game of life comes in here. So this is what we call a step in CnC. And it corresponds to some program written in some arbitrary language that can do some kind of computation. And we draw edges to basically the shared address space, or the shared memory, that various steps can work on. In this case, we only have one step here, and we're putting data in and getting data out. And these projection functions tell us what data to grab in and out. These steps, I'm assuming, are basically side effect-free things that get their data in and send the data back out. But if we just left it like this, CnC won't do anything, because we need to somehow tell CnC to spawn different instances of the step with different pieces of data. So to do that, we have this horrible thing that CnC calls a prescription, which is really just a run this thing call. And so this, you can think of this as like another a vector or just a big bucket of tags. And whenever we write an element to this tag, it's like saying spawn this life with that given tag, and all the data will be grabbed in, and then that one instance of that step will run. And we need some way to fill this tag up with all of the different pieces. So we're going to have a coordinate here. This will be our tag for each one of these different slicing points. So we might have one in here, and we'll have one here and here, which basically represent each of our different tile sizes. So we're going to have another step called gen, which will generate all of the coordinates for basically all the instances of life that we're going to run on each of these little tiles. So there'll be one tag per tile, and so one instance of this life step will get run for each of the tiles that we have. But gen needs something to run. And so in this case, we just create this empty arrow here, which says the single tag that we get in as an input is going to be run. And so gen will get spawned once. We'll do all this work, tag all of the other life instances. Life will now start working, and we'll compute this array, and then finally we'll get our results out. Now, the reason I kind of like this model is that we haven't actually said how any of the steps are going to execute. There's no ordering dependencies on how these steps execute. And there's no real ordering on how we fill up the data or anything like this. But if we left it at that and said just everything happen all over the place whenever we want, then suddenly we're just back to shared memory with a nice picture to go with it. So CnC adds one restriction in addition to that, is that these are all single assignment. All these arrays are single assignment. You can't write to a slot more than once. So this is going to have to fill up each array, but it can't go back and mutate one of its results that it computed prior to this. And that allows CnC to be deterministic, so that if you get a deadlock anywhere, you're always going to get a deadlock. If you write a program that can deadlock, it'll always deadlock. So this is a very flexible way of running. These steps run asynchronously. So you get a lot, unlike the normal way you might do fork joins, you're not restricted arbitrarily on certain boundaries. You can just spawn more instances. One of these steps could be computing up a bit more and always be one step ahead or so forth along this matrix. And depending on how we did our slicing, we might have one computing far ahead and one lagging behind or otherwise. So now is a good time to stop and ask questions here, if anyone has questions on this so far. Yeah.
Think of those frames that are there as windows. You're basically saying that there's stuff in each window
Mm-hmm.
simultaneously.
There could be, yes. So essentially, we're filling up. If you think of it as just a box, and we're filling up the box until we get to the top with a layer at a time.
But it's not really layer at a time.
Right. It's tile at a time. So we have these tiles that lay down, and we can tile certain ones up ahead of others. Does that make sense?
Yeah.
Okay, cool. All right. Any other questions on? Yes, yes. So this is basically it's a stream. It's a stencil program. So it's a class of streaming program. And this is the kind of case that we're looking to optimize. So that's why I use it as an example. Anyone else? Okay. So that's all well and good, but now how do we actually write that program? And so to do that, I'm basically trying to combine these graphs with the APL language. So The idea being that these graphs are not what you would normally see in a CNC paper. There's a lot more information in this graph, specifically these projection functions. These projection functions tell you, by looking at the graph, if you can know what these projection functions are, they tell you access patterns on the arrays that are at a deeper or more specific level than what you could normally get if you just didn't have these around. Or they're sort of at the subarray level. And APL is really, really good at expressing index patterns in its code. It's very easy to express pretty complicated access patterns on indices in a short amount of space and actually still have a hope of understanding it. I say a hope because you can always write bad code, and you can obfuscate your code quite easily if you do it the wrong way. But APL gives you some of these index accesses, so I'm sort of leveraging APL's power in this sense to make the expression of these projection functions concise, and concise enough that they could go along with the graph. And this was partly inspired by the 3-layer cake model, which is, I forgot who, I'm drawing a blank now on the name, but Art Drover? Okay, yeah. But basically, he presented a tier of parallel programming paradigms that started with data parallelism and then layered on top a form of process parallelism and then sort of layered on top an MPI layer that did the communication cross-node. And his argument was that at each lower layer you can get sort of tighter guarantees and reason about your code a little bit better. And if you really need the more power, you can jump up a layer and lose some of your ability to reason about your code, but gain the ability to express more rich patterns and processes. I didn't like the top 2 layers of the cake. I thought MPI and process parallelism were sort of arbitrary choices. And so when I saw CnC, I thought, okay, CnC can now be our top layer, so it's a 2-layer cake now. And from the APL side, obviously I like APL, but I wanted to push the language a little further because I wasn't happy with how you could describe your parallelism in APL. So I want to sort of push APL forward in the parallelism sector and give CnC a richer language to work with. So it would be nice if we can just take that graph and turn it right into code. And in a sense, we can. So let's see what that would look like. So I hope I have enough room here. So to start with, let's define this game of life again and see how it's changed when we turn it into a step. So it's still going to return some result, but this time all of the steps take in a tag as well as some of the data. And so we have that, and our tag, we're still going to need the neighbor counts here. And so other than this, there's not much that has to change. We still have to compute the neighbors, so we still have to do our sum. Like so. And we still have to compute the actual next generation. Okay. But now I'm going to assume that we're doing this game of life on a torus. And if we cut up one of these pieces and we're going to need additional information on the side. So we're going to need these are they called ghost cells? So we're going to need these ghost cells. So we're going to assume that the matrix we could get in actually has ghost cells around it. So we need to drop those off. And so there we just drop off the unnecessary ghost cells. And that becomes our result. But in addition to this, we have some annotations here. Specifically, we have to do these edges. Where does the data come in? And where does the data go out? So this is now our game of life step, as opposed to just a regular game of life program. We've added basically the edges, and our projection functions are here, which we'll define later. And then we've got the regular game of life, but then we have a little bit of extra code to be aware that we have ghost cells here. So now what does the rest of this code look like? So our program is going to have this global here, which is I'm going to call data. So that maps that to that. There we go. And in addition, we need to know sort of what the shape or what this tag looks like. So the tag is going to tell us the number of processors we're working on, the number of generations we're working with, and the rows and columns. And that's our initial tag that comes in. And based on that, we know what our data looks like, because our data is just going to be the generations, the rows, and the columns based on our input data here. So our input comes in there, and we grab the 3D version of that. We sort of expand it out. And in addition to this, our data needs to go out somewhere. And so this is our edge here where the data goes out. We basically grab the last generation and send that out. And then at this point, we're going to have to put in some stuff to compute the slice size? Something like that, yes. And we'll do that later. And then we're also going to have to define these tag functions at some point. But now we're basically done here. The only thing we need to do is actually prescribe or spawn off and run the pieces that we want. So to do that, we've got our gen step, and that's going to be prescribed from our tag. And if I wanted to be a little more precise, I could say there's some kind of function here as well, A, that's actually controlling how manipulating the tag before it gets to the gen. So we're going to spawn the gen on, this is a 1, the tag. So basically, all we're going to spawn it on is the generations, the rows, and the columns. We don't care about the processors for generation. And this forms the rest of our program. Ugh. Should be writing in cursive here, but. So let's see, do I have? Yes, okay. So let's define the tags here. Actually, I should ask, does anyone have any questions about how this is laid out and how this maps to the graph so far? Yeah.
So how do you deal with, maybe this is the compute slice size part, the fact that the tiles you're sending into your next generation function are slightly larger than the output in the overlap slice?
Yeah, so I'll cover that when we start computing the slice size. Okay. But yes, we are going to have to deal with that because they're slightly larger than what we expect. Okay, yes. So let's and well, okay, yeah. So now here there are two tag functions that we need, a put and a get, or P and G. So P and G, their main jobs are to generate the indices that we need to grab information in and out of data. So both of them are going to follow a similar pattern. So G, we know we're going to get the current generation column and other that we're working off of. And we know I've got a different function here. I'm going to assume we've got a function slice size to compute the size of our slice. based off of the current row and column that we're working on. And the reason we do this is because we may have a slice that's smaller than our maximum potential slice size in this program. So if we have one of these guys here, and this is not an evenly divisible number by the way we want to divide it up, we may get a really tiny slice here at the very end that we need to deal with. That may not be ideal, so we might have to write a better way of slicing it up, but that's the tuning expert's job, to do the computing all the slice size stuff and all that stuff, sort of thing. And this is going to have we're going to do something else here. And put is going to basically do that same initial piece. So in both of these programs, we're just sort of setting stuff up here. So now the question is, what are the indices we need to get from our matrix here? So if we have something like this, and we get a point in here, we know our slice size, ideally. We know our incoming point. And what we need to do is get all of the indices that might appear in there. And finally, we need to make sure that we're in the right dimension on the generation. So we have to make sure we're at the right generation. So we know that when we get them, we're going to grab it from the current generation. And basically, we're going to append that current generation to all of our local indices, our 2D indices. And we're going to have to compute the 2D indices. And remember, this is the question you were asking about the tile size being larger. So when we're grabbing in, we actually want to grab these ghost cells in as well as our regular cells. So we're going to have to wrap around on our system. So that's where the rows and columns come in. And we basically do a mod on that on our regular index size, which in this case, we're going to shift the row and column up one. Based, and our slice size is actually 2 in each dimension larger. So if this is our slice, we're actually going to, if this is our regular slice size, we're actually going to shift our dimension up and grab slightly around that. And that's our indexing function, yeah.
Is this grabbing single elements, or is it grabbing tiles?
So this is generating indices, which will then be used to grab a whole set at once.
Are they indices of tiles, though?
They're indices of individual elements that will then be used to generate the other stuff. Okay. And there are other ways to write this. We could have written this in here using different notations or other things like that. But it's kind of convenient to write them like this. So when we put the element, we're going to put it one generation forward. And we don't have to worry about all this wrapping around a ghost cell stuff because we got rid of that. So that leaves us with our basic tile there. And all this is saying is that basically we generate this as if we were a 2D matrix, and then we tack on the generation to each of these indices at the end. So now we've got a matrix of 3 tuples that all represent an index into those elements. And of course, we'd end the section down here if I had more space. So now we can get into computing the slice size, but does anyone have any questions at this point? Because this basically now maps, this code now maps pretty closely to what we have here. We just haven't defined gen. Nope. Have I lost everybody? I figure I might have lost a few people here. So we can revisit any of these pieces, or if you'd like to see something else. Yeah. But that's really the key idea of this whole thing. The computing the slice size is, I mean, if somebody's interested in seeing that, yeah.
I guess I'm still a bit confused that, you're using tiles as the basic unit of, say, your output, right?
Mm-hmm.
And yet when you're doing your indexing on individual elements.
Yes.
You have something else you're not showing that converts those into
this is the piece that does that conversion here, the in and the out.
Mm-hmm.
So basically, all these
Does G do that conversion then?
G. This is the function G here,
Yeah.
and all this does is this generates the indice elements, like a set that's then used to dereference the tile that we want. And
Right, but how do you know which tiles to get?
this is what we compute here.
I
So.
thought you said that computed indices of individual elements within tiles.
Right. So the result of this is a matrix that represents our tile indices all the way around. So it would be a contiguous region of all these things. There are other ways of representing this. Like we could say here something like data and then an expression here and here with there's 3 here. So we could do G here and then the rows and the columns generated here and here using similar expressions to this one here. So for example, if we had let me write this out. So we could say data, we want the generation, and then we want the rows. So if R, let's say R SR is our slice, then we could say R, which is our current row that we want. And we'd have to mod it over the maximum number of rows. So we've got the maximum number of rows modded over R plus the slice size of our piece. And this is going to generate a vector of, say we start at 2 and our tile size is 3, then it would be something like 2, 3, 4 here, assuming that it fits all within our range. And then we can do something here as well for the columns, which would look almost identical to this. And this is just a different way of expressing that same expression. Does that answer your question?
Wait, sorry, basic question. The in and the out go in kernel function?
Uh-huh. Yeah.
The symbols in and out go in kernel. That, how does the data flow into the developed pieces?
So these are, you can almost think of these as modules. They're entirely cut off from the rest of the world. So T and D and N are the only variables and only data that's visible in this whole system. And we bind D based on what is in. And R, the result of this whole computation is basically this. R is assigned into that.
And that's implicit because R is the first thing?
R is our return value of this expression. Now the reason it's done like this is I defined this life in APL, but this step doesn't have to be defined in APL. It could have been written in C++ or C or some other language.
So to get to Jeremiah's question, this block of code does expect what was it? So D and R to be matrices. So it is a vectorized piece of code that is dealing with more than one element at a time.
Yes, this piece is fully vectorized.
So
It's operating on a tile. This is a matrix here of some arbitrary size that it'll get in. And then it's expected that you have this as a vectorized code or something that's going to run really fast on that single processor.
Right, so my big question is that how do you generate that input tile?
Yeah, and that's,
Given that that's going to be multiple tiles from the in, that's going to be formed from multiple tiles from the input.
this won't be formed from multiple tiles. This corresponds to a single tile, if that makes any sense.
But that input tile is going to, because otherwise the tiles are going to get smaller every generation. Because the output of life is smaller than the input.
No.
Yeah.
Well, yeah, the input is smaller, but by a constant factor because we're expanding out the size down here by 2 each time, and we're shrinking it by. So basically, when each time we grab in something slightly bigger and we return something slightly smaller, and we set this into our data array here, and then we grab something slightly. So we have overlaps. The tiles overlap each other a little bit by 1.
Doesn't that mean you have to grab plus or minus 1 tile in each direction and then chop out the middle part?
So you're thinking of an underlying implementation, and it's possible that we might do something like that.
No, I'm talking about just the logic of this if it's passing around tiles.
It's not passing around tiles. It's passing around matrices that we think of as tiles, if that makes any sense. I think I'm missing your point. So we get in a piece of data, and if we can do an example.
How do you get in? I guess the thing is you're taking in an n by an n plus 2 by n plus 2 matrix and outputting an n by n matrix, right?
Yeah. So let's.
Somehow that n by n matrix has to turn into an n plus 2 by n plus 2 one.
Okay.
Generation.
So So let's say we have these two. This is our output, and this is our input. So then when I get this here, a 0, 0, this is my tile size. So then when I get it, I'm going to grab the data along here, and then down along here, and down along here as well as this. And that'll be my matrix.
And it knows that because?
Because I told it to compute that down here.
And so those are tile indices now?
They're indices into the regular matrix, but they're sort of aggregate. So if this is a 3, let's say this is a, down here is like 3, 3. The result of this computation here is going to be a matrix. And inside that, we're going to get, let's say we're computing the first generation, 0, 0, and then it's going to be 0, 0, 1, and then 0. Actually, we got 4 here, so it's going to be 4. So let's make some more room. Be 0. If this is 6 over here, then we'll say this will be like 5, and 0, 2. And then we just fill down like that along the rows. And that's what the result of this expression is, a matrix like this.
And then you divide that by the tile size to get?
No, this is our tile size. If we use this as an index, like if we took this and turned this into array indexed 0, 0.
Okay, but what is that array?
That array is data, our data array here.
So it's not, right, but isn't data an array of tiles? It's not.
No, it's an array of elements.
Okay.
Yeah. It's just a contiguous region of memory somewhere.
Okay.
Or, well, potentially contiguous. You can think of it as contiguous for here.
So it's basically the output is writing to a range of elements.
Right,
Data.
right.
It's not writing a single element, which is tile.
Right, no.
Okay.
And so I'm relying on the ability for us to analyze this and recognize certain patterns like that. And this is the meat of where my optimization concerns come in, is I need to recognize, for example, those tile sizes. I need to be able to adjust my memory layout based on those access patterns. And this is why I have this explicit, this is why these tag functions actually have to be an APL so I can actually analyze them and try to do that analysis. Whereas this part here doesn't have to be an APL. This could be in any other language you wanted. But I can't analyze it then. So I've lifted the access part, the pieces that are normally embedded in C++ code somewhere in a CnC program, and lifted that out to a language that I can analyze. Does that answer your question?
Yeah.
Okay.
I was following, I think I might have got confused. So when we got your augmented tile, you start with the 0th column and not the 5th column down there? It seemed like...
So this is the wraparound.
Right, and on the row wraparound? Okay.
Yeah, so it should be the 5th row. Yeah, you're right. There's one up.
5, 0, 1, 2.
Okay, I'm back.
Yeah, there's some stuff all around here to deal with, I think. But then when we actually do write out, we're writing to this little block here.
Right,
We take off the ghost cells when we write to it. And I should mention that this is all excessively preliminary. I mean, very, very preliminary. This is a sketch of how I might imagine this language working. If you guys have input on how to improve this or make it better, I'm all for it. But we should probably move on unless people want to see more of this program. I think I've got the program here if people want to see it, but we can do that later, I think. Let's see. I don't want to keep people too long. So the current status of this as far as hacking goes is I've got a rough compiler that no one should look at and that doesn't really quite work in APL and dialog. No, it's slightly worse than research. I couldn't even put the crapple on it. It's pretty, yeah, it's bad right now, partly because I keep changing the language. And so I'm still at the point where I'm changing this language around and changing semantics and things like that. And that does terrible things to your compiler. And what used to work, an hour ago, suddenly all the passes have to be rewritten or something like this. Right now, the runtime that I'm using to implement this is in Unified Parallel C, which is a partitioned global address space extension of the C99 programming language. And the basic idea is that it's a global shared memory model that works on SMP as well as you can use MPI as the underlying method or other things like that. So it makes a nice target right now. I don't know if I'm going to keep that depending on how my performance benchmarks go in the future. Where I'm going with this is there's one particular optimization problem that I'm working on with this kind of analysis, and that's the streaming case where I want to collapse the memory use. Since we're working in a single assignment system, if I want to generate 1,000 generations of the game of life on a, a 5,000 by 5,000 grid, it won't fit within simple, nice memory layouts, and I'm just going to keep expanding out my memory. So my memory usage just keeps going on. But if I can recognize, for example, that G plus 1 and G are the input and output to this data, then I can recognize that I can mutate part of that array and reuse the space without having to work too hard on it. And that saves me the time, the memory allocation, and so I'm working on trying to optimize that particular case. And the dialogue people are looking at this system and are interested in possibly funding this over the summer. So hopefully I will be working on this full time over the summer and have a nice, pretty system at the end of it that does all of this with great benchmarks and graphs and all sorts of fun stuff. And, I don't know. So some interesting questions that surround this is how formal can I actually take this language? The subset of APL that I'm using right now has been sort of axiomatized in one form or another in the past. But as I extend it, I'm not sure where it's going to break down there. How fast can it go? So I really don't have an idea of what are going to be the interesting bottlenecks as far as performance go here, partly because I'm not as experienced with that side of things. A question that came up in the CnC meetings on Wednesday was modularity and hierarchy. So there's a lot of talk on how do you compose these graphs together and how do you nest them one on top of another so that a graph is actually a step and so forth. And the existing solutions seem really complicated to me. But if we just think of a graph as having these single input elements and single output elements along these pieces, then composing these graphs is just a matter of linking these up and then telling it that that's a single step. And so a single prescription matches to a single tag prescription here. And so the prescription of a step matches carefully to the execution of a CnC graph. And those two work together, and it's easy to nest and some stuff like that. So that's a question I haven't explored very much, but I'm planning to do that sometime in the future. Additionally, from the APL side, being able to have the user extend the language in useful ways that the compiler can analyze. This is a question that the dialogue people are particularly interested in figuring out, and they have a system that is used to experiment with these features. So I might be working with that a little bit. And then something that interests me is I want to be able to extend this compiler, because you might not be able to get all the optimizations you think, but rewriting rules, these sorts of things would be interesting. How you incorporate this in nicely to actually programmatically extend the compiler for certain optimizations. So if I know that I've got a certain streaming case or something like that, how do I safely tell it that I can use this stuff? Maybe if I didn't program it in. So I'd like this to be, I don't want to have to bake in all of the different optimizations for all the different parallel programming systems that I can imagine. And I'd like to be able to allow the user to extend these sort of optimizations in a reliable way. Some of these optimizations would include sort of like the locality of data on different nodes, the memory affinity, vectorization at the node level. So right now my compiler just compiles to really idiotic C, and you'd want to make that C code such that it's easy to vectorize that code. And then of course, how are we going to schedule the steps, work stealing, dynamic scheduling, all these different approaches to how we schedule the steps on different nodes, how we do load balancing, these sorts of things. Interlanguage overhead. So if this step is actually written in another language, you want to eliminate any data transfer costs to get data to that step, make it run, and get the data back out into the main system. So it's important to be able to limit that. And then something that interests me is, can we do optimization by proof? Can we have these nice little simple graphs and then progressively, in a sort of formal way, move to a very performant implementation that can be connected in some tangible way to the original design piece, so that changes in that original design can either percolate down or identify maybe problems or things like this. So I think, in my opinion, CnC is actually quite easy to program in and quite easy to understand as soon as you get rid of all the vocabulary. You may disagree with me there. I hope I did a better job than the papers do. If I didn't, I failed miserably here. But I think that CnC and APL actually form a pretty nice combination for doing these indexing and expressing this access patterns at a high level. You may not want to write your main program. You may not want to write your game of life step in APL, but that's fine. I'm okay with that. And I actually like programming in this language. I think it's a parallel model that I actually find works pretty well for me, and I can reason about my programs a lot more easily here than either just data parallelism, or just fork join like maps and folds, or just these p-threads or this fork threading model or this spawning, where the interaction is not always as clear to me. So thank you. I think that's everything, and I'm happy to answer any questions.
So is this a pure subset of APL? Because I know APL does have.
Yes, it's a statically typed. It's statically typed. You are allowed to have side effects in certain regions. So like inside of a step, you're free to side effect things. But since the scope is restricted, you can't have side effects that percolate to the outside environment outside of that step. All global variables.
Do you have the state transform monad?
Something like that. I'm not really familiar with all those monads. So
You are, you just don't know.
possibly, very likely. But now that's also open to change. So it really, this is a, there's a question of, should I allow recursion in this, the index, the projection functions, or should I allow it but then not be able to do analysis on it? All the global top-level program is considered single assignment. So as soon as you assign a variable to something, it's bound forever. You can't change it or anything like that. So there's no mutation at the top level in the program side of things. The only place where you might get mutation potentially is inside of one of these steps. So it's pure in the way that I'm willing to go as far as pure is. I'm willing to push it farther in the purest direction or take away depending on what limitations I run into going forward.
I'm also curious, so in addition to whatever issues there are with respect to compiling APL code like this, do you have a sense for what additional challenges there are to compile this model efficiently? For example, the tag functions, on the face of it, produce, to get a tile, you would have to produce an entire matrix full of indices, which would then kind of trivially evaluate to that tile. So but the naive implementation would end up creating this extra data structure to represent a set of indices, and then doing a gather to dereference all these indices, and then making a new copy of the tile and populating it.
Right, right.
Which is obviously very inefficient as opposed to passing the pointer to the original tile.
Right. So part of the fact that since I know that this occurs inside of an indexing piece, I can restrict the domain a little bit, and I can do some more analysis on it. So just these functions here are fairly well defined. So I could actually sort of go through a proof to get a domain and a range for all of these indices. I could get a little set that I could, maybe like a constraint or something like that, and a range, and say these are in there now do whatever you want to do with that. Something like this might be easier to analyze because these are slightly, you might say these are slightly simpler, and I can do my dimensions, and I know these are going to be ranges. So the existing APL implementations are actually quite good at making this go quite fast. So one of the common implementation techniques in APL, if you want to get faster, is if you put a lot of your work in here to grab the data out, APL can optimize this fairly efficiently. There's still work to be done there. And
Does APL do the deforestation?
so in this sort of language, I think, and I'm fairly confident, that it's actually possible to statically determine the sizes of all the arrays and to statically determine the contents if you're sticking with integers. I definitely know you can get the sizes here. And so you can actually do deforestation throughout here. Something I didn't mention is there's no aliasing in this language. So it's not possible to have pointers that are shared between data structures. So this also simplifies things. Yeah, so that means that you can't, some of the things that get tricky when you start having pointers going all over the place are eliminated.
So for those of us who have no ability, are there any other questions? So for those of us with little ability to understand APL, how should we think of the capabilities that are present here, especially in your toy version of APL? So can we think of this as, one of the reasons I asked if it was pure is we could think of this as a pure, strict, call by value language with a library of matrix operations?
That's pretty close, yeah. I mean, the fact that I'm using APL notation here is largely a convenience on my end. You could write this in another syntax and get largely the same thing. There's as long as you're sticking to this pure, yeah, as long as you're,
where's the path and call by value length calculated?
Yeah. I mean, basically, it's in the libraries. So if you've got a good vector library, and then let's see, vector library, and then maybe like single assignment in places. You'd have to be able to enforce single assignment, but semantically, if you're willing to let that off, you're fine.
No, simple value oriented language can go pointers.
Yeah. Yeah. Does that answer the question? So I think the language, from a, like there's nothing really fancy going on here in terms of the language. It's just that there's a much richer vocabulary for talking about these things. There's a concise notation, and it's defined in such a way that I can actually do analysis on it. Yeah.
Does your analysis include like a dependency analysis to figure out what can, when you can, for instance, let some set of, if you imagine that there's a stack of tiles, you obviously can't calculate the whole stack of tiles up without calculating their neighbors, because
Right.
the previous generation would have calculated that.
Right.
So do you have something in there that's doing that dependency analysis to then say how I should schedule these things, or?
So at the moment, there are really two properties I'm hoping to be able to identify. One is this monotonicity of the indexing. And the other is that I can apply an ordering to the tags that prescribe a given step with this monotonic approach. If I can apply that ordering and relate it to the monotonic indexing, then I can schedule it in a streaming pattern way. Yeah. But, yeah. So those are really the two optimizations I'm looking at right now.
So there is sort of a further restriction on the language here that you do have this monotonic.
So the data structures at the top level are monotonic. Yeah. Inside a step, I don't restrict that right now. So the inside of a step, you can mutate, you can do all sorts of stuff in your local state. And I can still actually reason about that fairly well because I don't have this aliasing around. Right. So when you assign something in, you can either prove that you can just do the pointer change, or you make a copy. But also this could be any other. This could be C++ code. So that's really where the restrictions come in, like the single assignment. These other things. It's the tag functions and the top level. Because if I get rid of the single assignment properties on the top level, then I've blown my determinism. So. And also, of course, I've changed CnC to use arrays instead of arbitrary data store collections. But, I mean, I did that mostly so that I can make sure that my indices are going to be in integers, basically, at the bottom level. So I don't have to try to analyze symbols and figure out how to apply an ordering to symbols or something like this. Any other questions? Thanks a lot.